Imagine a future where your thoughts directly control advanced prosthetics, communicate with computers, or even help restore lost sensory functions. Brain-computer interfaces, or BCIs, hold immense promise for revolutionizing how we interact with the world and overcome disabilities. Yet, like any sophisticated technology, they face significant hurdles, with one of the most critical being the omnipresent challenge of signal interference. Unmitigated noise in a brain-computer interface system leads directly to a severe degradation in performance and reliability, effectively rendering the device functionally useless or even potentially unsafe. Without proper handling, these unwanted signals can completely obscure the subtle neural commands a user is trying to convey, turning a potentially life-changing technology into a frustrating and unpredictable experience. The core reason unmitigated noise is so detrimental lies in the inherent weakness of the brain's signals we are trying to capture and interpret. Neural activity produces incredibly tiny electrical potentials, often measured in microvolts, which are easily dwarfed by external interference. This interference can come from many sources, including muscle movements like blinks or jaw clenching, electrical artifacts from power lines known as line noise, and even signals from other physiological processes like the heart or sweat glands. These extraneous signals drastically reduce the signal-to-noise ratio, making it incredibly difficult for decoding algorithms to accurately discern a user's true intent. When noise is not addressed, the practical consequences are immediate and severe. Users experience erratic device control, where intended actions are either delayed, misinterpreted, or completely ignored. This leads to profound frustration, diminished user confidence, and ultimately, a rejection of the technology. For medical applications, this could mean a prosthetic limb performing an unintended movement or a communication device failing to convey a critical message, posing real risks to user safety and well-being. The system effectively becomes a random signal generator rather than a precise interface. A key concept here is signal purity, which refers to how free the neural data is from contamination. Researchers employ advanced techniques such as common mode rejection, specific digital filtering, and adaptive artifact removal algorithms to enhance this purity. Without these sophisticated processing steps, raw brain signals are essentially a cacophony of electrical activity. For example, electromyographic or EMG, noise from facial muscles can be thousands of times stronger than the tiny electroencephalographic, or EEG, signals from the brain, completely masking the data of interest. Properly addressing these issues is not merely an improvement, but a foundational requirement. Ultimately, the thorough and systematic mitigation of noise is not just a technical optimization but a fundamental prerequisite for the very viability and adoption of brain-computer interface technology. It is what transforms raw, jumbled electrical impulses into meaningful, actionable commands, ensuring that these innovative systems can reliably and safely fulfill their promise of enhancing human capabilities and improving quality of life.